Welcome to Thermal Engineering Concept and Principle. This is Professor Ali Tarra. What do you know about vertical heat exchangers and their philosophy of operation with geothermal heat pumps? We mean here the operation of the borehole geothermal heat exchanger. To know that, come with me to go through details of the present episode. Welcome, my friends and colleagues, to introduce the aspect of thermal design for the boreholes in a geothermal heat pump. In this episode, I will introduce the characteristic of a borehole heat exchanger and its installation in the ground, accompanied by its main components to construct a heat exchanger that is called borehole type, which is a vertical heat exchanger. In this part, I will cover the construction of the heat pump itself and the borehole and how can we estimate the depth of the U-tube in the ground, which is related to the properties of the geological aspect for the ground and the thermal properties of the grout or filling that is surrounding the U-tube in the ground. Thank you for continuous support and let us keep on this series of videos in this field, which is the renewable energy source called geothermal energy. The objectives of the present episode cover the geothermal heat pump components. The main components, of course, I will pass through. And then we have the direct contact geothermal heat pump, which refers to the contact between the heat exchanger, which handles the circulated fluid in the heat pump and the ground. Then we will go through the estimation of the depth for this heat exchanger, which is in effect, we are calculating the surface area of the heat exchanger to achieve a certain heat or cool load. And finally, we will approach, as usual, the closure for the present episode. In this system, we have the heating mode, where Earth works as an energy source to the fluid which passes through the borehole in the blue direction, which extracts energy from the ground and then return back to a heat exchanger
which is a part of the heating pump. Then this fluid will give energy to another circulated fluid, which we have explained in the previous slide, and then that will provide energy to space. In that way, we have extracted energy from Earth and transferred to the, for example, domestic use in this example. Then heat can be transferred from ground to the utility. In this case, we have the utility as heating for um, house or maybe in a restaurant or other applications. So this is the heating mode, how the heating mode operates. Here we have a vertical heat exchanger, which is called borehole heat exchanger, that is installed vertically inside Earth. It is composed of uh, YouTube, and the YouTube is installed inside a bore surrounded by grout material, and this grout material should be conductive material to facilitate heat transfer and conduction between the soil, the external part as shown in this figure, and the tube itself. So in that sense, we are uh, extracting energy from the soil, which represents the earth structure, conducted to the grout, through the grout material, to the tube surface, all of that in conduction, and then by convection to the fluid which is passed inside that U-tube, and it could be water, shown in the right hand side photo, water inlet and water outlet. Water inlet representing the blue one, and the outlet is the green one. So hot fluid or hot water, we will get it from that bore hole, and can be used for heating purposes. Almost similar system can be used for cooling system as well.
Here we have the condenser, which represents the fourth main part of the heat pump itself. So we have the underground heat exchanger, the borehole, represents the condenser, and the other parts which compose of evaporator, compressor, and expansion valve, represented by the other side, which is out of the ground. Then what we have, the ground part represents a condenser. Here we have the refrigerant vapor, which is circulated in the heat pump, passes through the inlet part of the heat exchanger through the red line, and then it reject energy to the ground, of course, through the filling or the grout to the ground, and then returns as a liquid refrigerant to complete the closed circuit of the heat pump. Again, this is a DX geothermal condenser because we didn't need an intermediate fluid to transfer energy to the ground, because the main principal part, which represents the fluid that is circulated in the heat pump, is the liquid which passes through the heat exchanger. Borehole, uh, depth estimation. In this episode, I will introduce another relation which has been derived and published by me to find out the depth of the geothermal heat exchanger. Let us consider a U-tube with specified dimensions, denote S sub P, which represents the distance between the centers of the two legs of the U-tube, and borehole diameter. Let us find an equivalent diameter from the assumption which has been based on the idea of keeping the volume of the filling or the grout is constant in both geometries, the equivalent and the original configurations. So this assumption will produce the equivalent diameter of the tube to be square root of 2 times d naught, as represented in equation number 1. And this equation has been derived by many investigators in the open literatures and can be found even in the present reference of the present correlation. And let us transform the equivalent tube to the form which is shown on the right hand side of the above illustration. And to keep the shank distance between the original and the equivalent geometries constant. That is d sub s equal s sub p minus d naught, which is equal to s sub p e. E here refers to the equivalent minus the equivalent. And with some analysis and interpretations which have been described in the original paper, we have arrived to L sub PE nearly equal to L sub P plus 0.207 times D naught as represented in equation number 3. And L sub PE represents the distance between the center of the equivalent diameter and the center of the borehole. And in that case, we will get an offset or eccentric cylinder in the outer one. Then we may calculate R sub F in the form of equation 4, which has been already mentioned in the previous episodes and can be found in textbooks such as Holman, that is heat transfer, and even in the reference of the present model, you may find this equation as well. And the reference is presented in the list of the references, which is situated at the description box below the video of this episode. To verify the present model, let us consider a heat pump with a geothermal condenser which is in the form of a single vertical U tube. And the condenser circulates the Freon R410A in the heat exchanger and the geothermal heat pump with a condensation heat transfer coefficient of 3000 watt per meter square degree centigrade, and it will be considered as a typical reference value. The copper tube has the same diameter for both legs, and 12 geometries will be considered in this example, with diameters 9.53, 12.7, 15.88, and 19.05, with different values of alpha, which represents the constant of the tube spacing, B sub B 65 millimeter, 75 millimeter, and 90 and 100, with the other dimensionless parameters as shown in this table. And a range of thermal conductivity between 0.73 and 1.9 watt per meter Kelvin will be used to show the effect of thermal conductivity of the grout on the performance of the geothermal heat exchanger. We have delta T mean equal to T fluid minus T soil. And here for the condenser, we have T fluid corresponds to T condensation, which is a constant value. And we will assume a value of delta T mean equal to 14 degrees Celsius. The ratio WF tube wall factor, defined as D naught by divided by T, which represents the thickness of the tube wall. And we have the S sub P equal to alpha D naught as represented in equation number 5. That is the relation between SP and D naught in the form of SP equal to alpha D naught, and alpha varies between 2 and 3 as shown in the table. To estimate the total thermal resistance of the borehole, let us consider this single tube arrangement where we have refrigerant vapor enters the heat exchanger at one leg and leaves as a condensate on the through the second leg, and then it will be called the DX geothermal condenser in a heat pump, as there is no intermediate fluid to be circulated between the heat exchanger and the rest components of the heat pump, because only Freon will be circulated between the heat pump and this heat exchanger in the ground. And R sub B equal to summation of R sub F plus R sub P, and we have defined R sub P as the total specific thermal resistance of the pipe, which composed of two components, the convection part, and the second part is represented by the conduction part as shown in equation number 7. And to get the total thermal resistance as a specific value, we have R sub B plus R ground. And R ground is usually a dependent variable on the time, because the conditions are varied in the soil with the time, but equation 8 can be represented with a constant value of R ground because it has been found that after 1 year of operation for the heat exchanger, the geothermal heat exchanger, then the soil will heat transfer performance will reach steady state conditions with R ground equal 0.053 meter Kelvin per watt when the thermal conductivity of the soil was 2.42 watt per meter Kelvin. Then the heat loading equal to Q equal delta T mean divided by R total in watt per meter. And then we may find the depth of the heat exchanger by dividing Q dot condenser divided by the heat loading as shown in equation number 10 in the units meter. And the Q condensation will be calculated from the condensation of Freon R410A by multiplying the mass flow rate by the latent heat, and that will be represented in equation number 11. From these equations, we may estimate the Q value, in fact, which represents the heat loading of the heat exchanger. Results comparison of the present correlation and compared with other available correlations in the open literature, we have here the geometry as represented by G1, where the tube diameter 9.53 millimeter, D bore equal to 65 millimeter, and SP, the spacing between the legs of the U-tube, equal to 3 D naught. And this illustration shows that the maximum is predicted by Bose-Etal correlation, and the minimum is predicted by Koenig equation, and in between the rest of the models. Here we may find that Gu and O'Neill and Tarrad reference star, Tarrad star, they predicted almost the same values, and the present work, the blue line, occupies midway between the maximum and minimum value, and Remond, then we will go to Sharkawi, which is the nearest to the Koenig correlation, and we have compared it with other correlation which has been predicted by Tarrad double star, and Tarrad double star represent the reference number which will be found in the list below the video in the description box. All these correlations show that the trend showed that the trend of these values showed a decrease in the borehole resistance, the specific borehole resistance, as the thermal conductivity of the filling was increased. We have almost the same behavior for the geometry G4 when the tube diameter 12.7 millimeter, D bond bore equals 75 millimeter, and SP3 D naught. And again, it showed the same variation as the thermal conductivity increases. The thermal resistance or the specific thermal resistance of the borehole showed a decrease, and the highest was predicted by Bose-Etal, and the minimum was predicted by Koenig. Here, this will give you an indication how the choice of the correlation specify the depth and affect the cost of the heat pump. Therefore, we should take care about the accuracy of these correlations when we want to select any of them. Here to show the effect of the diameter with a constant value of dB equals 75 millimeter and SP equal to 2D naught. As the tube diameter reduced, then we will get a higher borehole resistance, because as the D naught is reduced, the filling resistance will be higher, and vice versa. Then at diameter equal to 19.05 millimeter, as designated by G9, will be the minimum, because the tube will be closer to the outer surface of the borehole. And to show the effect of the spacing on the overall borehole resistance, here we have this figure where at SP equal to 2D naught, G6 has higher resistance, and as we increase the spacing, then we will reach a minimum at SP equal 3D naught at constant D bore. And the thermal resistance is reduced because the tubes will be closer to the outer surface of the borehole, and hence the resistance is minimum. The borehole heat loading, when we use the results of the geometry at 9.53 millimeter tube size and dB equals 65 millimeter with variable tube spacing, then we will get the higher heat loading when SP is a 3D naught, and the minimum will be at SP equal to 2D naught. And these behaviors of the results show that increasing the thermal conductivity will increase the borehole heat loading, because when you increase the spacing, then we will reduce the total thermal resistance of the borehole itself. And similarly, we have another design when the geometry composed of 12.7 millimeter tube size and the bore equals 75 millimeter for different tube spacing. Again, we have got the same behavior. The maximum will be obtained at the higher SP and higher thermal conductivity, and the lower will be obtained for lower value of thermal conductivity and lower space tube spacing, as it equal to 2D naught for geometry G6. We have the maximum tube spacing inside the borehole, SP max, equal to 0.75 D sub B minus D naught, and this equation should be used as a general guide when you select the tube spacing, because if you choose high values of tube spacing, you may situate the tubes close to the outer surface of the borehole. Then in this case, we are destroying the borehole itself, because it will not be able to resist the design, and in that case we will lose the advantage of using the grouting material in the borehole. My friends and colleagues, we have arrived to the final part of this video, which is related to the closure. We passed through the geothermal heat pump components, the underground part, which represents the borehole, and the other parts, which are on-ground parts, which includes compressor, expansion valve, and either the evaporator or the condenser for the direct geothermal borehole, where we have the fluid passes through the tube, the U-tube, and is the same fluid which is circulated in the heat pump itself. And that's what we call the direct contact geothermal heat pump. And I used one of my published correlations to predict the depth of the single U-tube, and it was compared with other published correlations for specific conditions of the heat load and the physical dimensions of the borehole. There are some valuable references you may find in the link in the description box for some references which are either used in this episode or in you may increase your knowledge about geothermal energy with the others. And usually I put the reference which has been discussed in this episode as the first reference in the list. If you feel that the information and the thermal design is useful to you and others, please subscribe to the channel and share it with your friends, and we hope can achieve the main goals of our for the creation of our channel. Bye-bye.